So the way that we do this, almost all the time, that works the best is you start by guessing a mass flow rate, and once you've guessed the mass flow rate, it's usually very easy to get the pressure drop through a duct or any sort of series of ducts or any network of pipes, right? But you guess the mass flow rate, and then you, if you had a pump, which you will in your homework, you'd be able to, based on that mass flow rate, figure out what pressure rise the pumps give you, and then you'd also be able to figure out what pressure drop the duct is going to exhibit, and you'll have to adjust the mass flow rate until those two quantities agree, right? So we're going to do that here, right? We're going to guess the mass flow rate, and once you have the mass flow rate, you can calculate the Reynolds number, right? So the Reynolds number is the density of the fluid. We're using the average density multiplied by the hydraulic diameter. The hydraulic diameter of the channel is the inner diameter of that conductor, multiplied by the mean velocity divided by the viscosity. The mean velocity here is the mass flow rate divided by the density and the cross-sectional area of the channel, right? Again, the mean velocity is the single velocity that represents what mass flow rate is being carried through that channel. All right, so here's the Reynolds number. We know that the friction factor is a function of Reynolds number, L over D, E over D, so I got to know something about the roughness of the channel, and then the duct shape. In this case, my duct shape is round. It's just a pipe, right? So I can now have to decide, do I want the average friction factor or do I want the local friction factor? And of course, in this particular situation, I want the average friction factor because I'm interested in calculating the total pressure drop across that duct. I don't really care about what the local pressure gradient is anywhere. I want the total pressure drop across the duct. So I get the average friction factor, and then that allows me to calculate the total pressure across the duct using this equation. This is just a definition of the average friction factor. And, unless I'm really lucky, the value of the mass flow rate I guessed here is not going to give me exactly 4 kilopascal. So I'm going to have to then, adjust the mass flow rate until this matches up with my pressure source. We'll let ease help us with that. So let's go look at how this works. So here I guessed 1 gram per second mass flow rate. These are the calculations I laid out. So this is the cross-sectional area for flow. This is the mean velocity. This is the average Reynolds number in the pipe. And then I got to access the correlations, right? So I go to options, function information, heat transfer. Let's go find convection. We'll come down here. I know I want an internal flow correlation. I want either the non-dimensional average, which is this top one, or the non-dimensional local. And I'm going to get the non-dimensional average. So I click on that. And then I would scroll through here until I found the duct shape that I want. In this case, it's the first one. It's round. So I would paste this in there. I've already done that right here. So this is calling that. Give it the Reynolds number. Give it the Prandtl number. Give it L over D. Give it the roughness. I'm assuming that my duct is aerodynamically smooth, so the roughness is 0. What does it give me back? It gives me back the average Nusselt number assuming constant temperature, the average Nusselt number assuming a constant heat flux, and then it gives me back the thing I really care about right now, which is this average friction factor. Then I can use the average friction factor to calculate the pressure drop. And if I do that, what I should see here is that the pressure drop I calculate is 18.6 kilopascal. The pressure drop I actually have is only 4 kilopascal. So obviously the mass flow rate that I assumed here is quite a bit too big, right? So what I'm going to do now is update my guesses. So I'll click the little G button, and I'll hit yes, and I'll come in here and I will get rid of this guess, and then instead of having that equation, I'll add an equation here that forces this calculated pressure drop to match the actual pressure rise of my dewar. And if I hit solve, yeah, so now these two pressures match, and the mass flow rate that causes them to match is, I don't know if this is cut off, but it's 0.4 grams per second, right? So that's that part of the problem. Probably a good idea to update my guess values again. Now let's go back and do the next thing. So I know my mass flow rate. the next thing I probably want to do is actually figure out what is the outlet temperature of the vapor, right? So the vapor flows through my duct, right? And I know that because it's being exposed to this thermal energy generation, it's probably being heated up, right? It'd be nice to know how hot it gets. And so, we go back to the energy balance, which I have right here. Right? These are the two forms of the energy balance. This first one is pretty useful looking to me because I know the heat flux is a constant, at least that's my assumption. So I'm going to take this one here, and that's what I have here. I'm going to try to solve it. It's pretty easy to solve in this case, right? It won't always be that easy, but in this case it's really pretty easy. I just put the dx term over here, and I have dt over here. I integrate both sides. The heat flux is a constant, so I can pull that out, and I get this equation here, which just says that the outlet temperature is the inlet temperature plus this is basically how much energy did I pump into that fluid divided by m dot times c. Right? So let's go look at what that looks like. So that's what I did right here. This calculates my exit temperature. If I hit solve, what I find is that my outlet temperature is 232.9 Kelvin, right? So now is the time where I can actually go back up here and instead of just guessing what the average temperature is, now I can actually use the right average temperature, right? So the average temperature is the inlet temperature plus the outlet temperature divided by 2. Of course, doing this is going to change everything. So I just updated my guesses so that hopefully this will converge, and it does. And it actually changes things a little bit. My outlet temperature is about 195.8, right? So where am I at now? I know what the flow is. I know how hot the vapor gets. I know that at the exit, the vapor is still only about 200 Kelvin. So that seems pretty cold. That's not the temperature, though, of the actual conductor material, right? So I ought to start thinking next about how hot the conductor gets, right? So this is the case we talked about the other day where, I have a constant heat flux. So if I think about the mean temperature, I go in here at like 77.8, and I just decided that I heated it up to about 200, right? But the surface temperature, which is the conductor temperature, is hotter than this mean temperature. So what I really want to know is how hot does the surface get, right? And that's where I start to think about the heat transfer coefficient. So the heat transfer coefficient, it starts really high at the inlet because I have a thin boundary layer, and then over some region, the thermal entry length, it drops down and eventually becomes constant, right? If this is a turbulent flow, I would expect this to happen very quickly. If it's a laminar flow, it might happen over a longer length. But whatever, certainly the heat transfer coefficient gets worse as I move through the duct. And what that means then is that this temperature difference between the surface and the fluid is going to get larger and larger, right, until finally it hits this constant value, right? So if I'm looking for the hottest spot in the tube, I'm really looking for this temperature right here. I'd really like to know what is the surface temperature right as the fluid is leaving, right at the outlet of my conductor. So that's the next thing I'm going to try to calculate. And to do that, what I need is not an average heat transfer coefficient. I actually want what's the local heat transfer coefficient right here, right? And actually, I can do better than using the average properties. I'd really like to use the local properties right here, right? So I'm gonna do that. I'll use the fluid properties right at the exit, right? So this is all the fluid properties at the exit, evaluated at the exit pressure, which is just P ambient, and the exit temperature, which is like 195 Kelvin. So I'm going to calculate the Reynolds number, right? Same calculation. Now I'm just using the outlet density and viscosity and the outlet mean velocity, right? So I'll calculate that with the outlet density. I'm going to use the correlation for local Nusselt number, right? So this is my local Nusselt number. It's a function of the Reynolds number, which I just calculated. X over D, so I want it at the outlet, so that'll be L. This is my roughness. My duct shape is round. The Prandtl number is a property. The thermal boundary conditions for this problem are pretty obvious, right? The thermal boundary conditions are constant heat flux. Once I have this local Nusselt number, I can get the local heat transfer coefficient right here. And finally, I can calculate the temperature of the conductor material right at the exit, right? And that's what I did right here. So if I go back here, look down here, that's what these calculations are, right? Here's getting all of my outlet properties. This is the velocity, the mean velocity at the outlet. This is the Reynolds number at the outlet. And then here, I have to be careful, right? I have to actually go back and call the correlations again, right? So I go to options, function information, convection. But now instead of using the average quantities, which is this top one, I'll use the local quantities, which is this bottom one, right? So that's what I did here. This is getting the local heat transfer coefficient, and this is the temperature of the conductor. So at the outlet, the fluid temperature is 195.8 Kelvin. The surface temperature, though, is quite a bit hotter than that, right? It's 314.4 Kelvin. So, you know, somewhat hotter than the fluid. Still not hot enough that I think it's in danger of melting, right, if it's any reasonable material. So that's good news. The last thing I probably want to think about, though, is that the hottest spot actually? So, you know, we just calculated the temperature of the material right there, right? So that's the hottest surface temperature for sure. But if you think about it, you know, there is some resistance radially to getting the ohmic dissipation from the outer radius to the inner radius. And if that's a substantial resistance, then this temperature here might be significantly hotter than this temperature here. So to be safe, I had to think at least a little bit about what this temperature is. And we can do this, you know, very formally, where we derive the differential equation and all that kind of stuff, or we can do it a little bit more relaxed, where we just think about the resistance to conduction here. So the resistance to conduction in the radial direction is given by this equation here. The total ohmic dissipation is given by this equation here. If I just want to estimate as to how much this temperature will rise, I'm going to force all of this ohmic dissipation through this resistor. That's what I did here, and figure out the temperature rise from the outer diameter to the inner diameter across the conductor, right? This is going to be conservative. My actual temperature rise will be less than that. So let's go look at that. I did that right here. My DT radial is pretty small, right? So DT radial is somewhere, where is it? Right here, 0.73. So I'm not getting much of a temperature rise radially across my conductor. I'm not too worried that the outer part of it's getting that much hotter than the inner part, right? So you know, everything looks pretty good from that standpoint. The reason I don't get much of a temperature rise radially is because this resistance to radial conduction is really small. It's only about 0.01 Kelvin per watt. All right, so the last thing I'd like to do before I call this good, is decide whether or not my my assumption that the axial conduction along this conductor could be neglected, right? So when I do that, what I'm basically saying is that if I'm a piece of energy that gets generated sort of right here, my least resistance path out of here is to go radially across the conductor. We know that's a pretty small resistance path, but then convected to the vapor, right? Versus to go axially, right, to get more area for convection. So if I'm a piece of energy, would I rather go like this radially, or would I rather go back and forth this way? And the way to think about this is, how hard is it to move axially versus how hard is it to move radially, and how hard is it to be convected from the surface? So these are all resistances that we can calculate. We already calculated this guy, the conduction in the radial direction. It's about 0.01. We can calculate our convection, right? 1 over h bar times the perimeter times the length. That's the resistance to convection from the surface. And we can calculate our conduction axial. That's just L divided by K, and this cross-sectional area is the cross-sectional area for heat to travel in the axial direction, which happens to be the same as for current to travel in the axial direction. So I'm looking basically at the ratio of these resistances, and I'm going to decide, is this a big resistance? Because if this axial resistance is a big resistance, then I did a pretty good job in my assumption, right? Nothing's going to want to move this way. But if this is a small resistance, then my assumption isn't very good, because it's pretty easy to move this way, right? And of course, nothing is big or small by itself, I have to compare this axial resistance to convection, right? So let's go do that last thing. And I did that here. So here's our conduction in the axial direction. Here's our convection. And if I divide these two, what I'm going to find is that our conduction in the axial direction is quite a bit higher. It's like 50 times higher than our convection, right? Our convection divided by our conduction is, where is it? Right here. Our convection divided by our conduction is 0.02, right? You can see that our conduction in the axial direction is like 90. Our convection is like 1.8, and then our conduction in the radial direction is really small. So, if I'm a piece of energy, my best, easiest path is to go straight out and be convected to the fluid. I'm really not going to be that interested in going up or down. That's not an easy path for me to take, right? So that is the limit where I basically have a constant heat flux. Now, if I would have done the same calculation and I would have found that our conduction axially is like 0.01, so it's substantially smaller than this one, then I have a problem because my assumption is wrong, right? Then I have the situation where the opposite thing is going to happen, and that is that my entire current lead is going to want to become isothermal because it's easy for energy to move back and forth axially. And I have a situation now where my boundary condition really should have been constant temperature. I would have a constant temperature current lead. Okay, so that's an example of an internal flow problem. I think it's a pretty good example of a single fluid traveling in a duct. Certainly it's enough to get you to the point where you can do your homework. What we're going to do next is kind of a brief introduction to heat exchangers, right? And heat exchangers follow naturally from internal convection because heat exchangers are all about internal convection, but they're more complicated than what we just did because instead of having just one fluid flowing, you have two fluids flowing and they're communicating thermally with each other, right? So you've got energy balances like we just did, but two of them, and these two energy balances are actually coupled together, right? So heat exchangers are pretty cool, but they're also a little bit more complicated. So that's what we'll start talking about next.